Hello, today we will discuss about a new global constraint that is the alldiff constraint. As you can see in this constraint, we want to assign values. Here is represented with the colors on the parrots. We want to assign different colors to all the parrots, assuming the parrots represent the variables. That's a very useful constraint that we already met in several problems, such as the quadratic assignment problem, or the Sudoku problems, or the n-queens problem. Okay, but you may also find it in the vehicle routing problem and so on. So very useful, very important constraint. So it's quite important to also understand how it works, what is the filtering that is performed for this constraint, and the different alternatives. So let's start first with the definition of the constraint. The semantic of this constraint is this one. You are given an array of n variables, and you want that for every pair of variables, for every ij, okay, such that I is different from j, you want to have different values assigned to these variables. Okay, you want these variables to take different values, as each s is expressed here. Okay, so how many binary constraints? So this is a binary constraint because we have variables involved in these small constraints. How many binary constraints do we need to enforce the global alldiff constraint for an array of n variables? Of course, since you have to enumerate every pair of variables, you have order of n square binary constraints, small binary constraint that you need to post in your model to enforce this global constraint. Okay, and the goal of this series of video is to show you that we can do better than just posting these small binary constraints. So, if you want to enforce the alldiff with small binary variables, you can do it this way. Okay, so this is the not equal constraint for the binary form involving two variables x and y that you have here. Okay, what you will do is that as soon as one of the two variables becomes bound to a value, you will remove this same value from the other variables. And this is what we do here. If we realize that y is bound at the time of the posting, so at the time of the posting, when you are stating the constraint in your model. So if you realize that y is already bound, then you can immediately remove the value of y. So you just take the minimum, you could take the maximum, but you know that it's bound, so the minimum and the maximum would be the same. You take the value of y and you remove it from the domain of x. In the other case, if x is bound, you do the other way. You remove from y the value of x. And then this is the most general case. It means that at the time of the posting of the constraint, none of the variables is bound yet. And so you will just say that you would like this propagator to be notified whenever one of these two variables becomes bound, x on y. And so the propagate method here will be executed, will be called by the solver if one of these two events occur. Okay, so if x or y is bound, then this propagate method will be called, and we do exactly the same as the two previous cases. Okay, with just one little detail, but that is quite an important one, is that we will deactivate the constraint in case of one of these two situations happen. And the optimization is useful because assume, for instance, that y becomes bound, then you remove the value of y for the domain of x. So let's say that y is currently equal to 2 and x is equal to, the domain of x is 2, 3, 4, 5, 6. Okay, so you will enter into this case, y is bound, and so you will remove from x, you will remove the value 2, exactly like this. But you surely don't need to be notified again when when the variable x is further bound during the search, because you know that there will be nothing else to remove from the domain of y because it has already been removed from x, the same value. Okay, so assume, for instance, that later we have that x becomes 4, then you would need to remove 4 from the domain of y, but you know that it's not possible already. And this is the objective of this small optimization. We just deactivate the constraint to say to tell to the solver, please don't call this propagate method any further based on these two registration here. Okay, we want to be deactivated. And if you remember in the solver itself, so in the solver itself, the way this flag is used is like this. So when the constraint will be scheduled, we always do a check to verify that it's still active and that it's not yet scheduled, of course, because we don't want to have 2 times the same constraint scheduled twice. We don't want the same constraint to be scheduled twice in the propagation queue of the solver. But if it's not active, and only if it's not active, and this is a required condition to be added to the propagation queue. Okay, so this is why this small optimization here can help a little bit the performances of this binary different not equal constraint. Okay, so now we can see what happens if one of the variables, so we come back to the more general situation where we have n variables, and we can see what happens if we have one variable that becomes bound.